And again, welcome to today's webcast, Best Practices in Architecting for the Cloud. Our presenter today is Jeff Barr, Senior Evangelist at Amazon Web Services. Jeff has been with Amazon for 11 years. So Jeff, you have the floor.
All right. Well, thank you all for coming. Good morning, good afternoon, or good evening, wherever you happen to be, and welcome to the webinar. In the time we have together today, I'd like to give you some guidance and some advice that will help you to build some powerful, scalable, and highly resilient cloud applications. I would like to let you know I really appreciate the time you've set aside from your day in order to attend. I really hope you'll find this webinar to be of value to you. As you heard in the introduction, please enter your questions and your comments as we go. I'm going to be monitoring those on my screen as I present, and then I'll do my best to address some of them as I go, and the rest I'll take care of at the end as time permits. I'm going to assume that you have some basic knowledge of AWS, but I will provide some brief intro to some of the services as I go. If there are some things that I mentioned that you don't recognize, please do feel free to visit AWS.amazon.com for more information. So we're going to talk today about a number of different cloud best practices. And a lot of the information here comes from a white paper that was originally written by one of my colleagues by the name of Janesh Varya. This white paper is available on our website. You can go to bit.ly/AWS-best-practices to download the latest version of this white paper. This is an extremely detailed white paper. It's about 23 pages long. There's quite a bit more information on there than I can cover in the space of an hour. So I definitely would advise you to take a look at that after the webinar in order to go in even more depth into the things that I've talked about today. So let's talk about, to get started, why do cloud architects actually love the cloud? What are the interesting attributes and what are the reasons that architects have been flocking to the cloud and look at it and say, this is interesting, this is cool, this can help me to do my job better, faster, and less expensively? The first concept that comes up is the idea of abstract resources. So with abstract resources, you think more in terms of virtualized entities, such as instances instead of servers and volumes instead of hard drives. Unlike the typical IT environment of the past where you pretty much had a fairly small selection of different sizes and shapes and performance points and storage levels of the different components, you have a wide variety of different instance types and performance levels available to you in the cloud. So one really interesting principle to think in mind is that you can actually shape your hardware to fit your application, having to force fit your application to fit the hardware. You can pick and choose exactly what you need and when you need it. So you can effectively late bind your hardware to your application, choosing the most effective hardware for any particular release of your application. On-demand provisioning. So this means you're going to be able to ask for exactly the resources that you need, exactly when you need them. You'll use them for as long or as short of a time as you need them, whether that's effectively in perpetuity, you allocate them and use them for the entire lifetime of your application, or maybe it's in terms of minutes or hours. You need transient resources. Maybe you need some extra disk volumes to do some kind of data processing or a big sorting job. You can actually allocate those volumes on an as-needed basis, attach them to your instance, do that sorting. When you're finished, copy off the data, release the volumes. So this idea of actually thinking dynamically and thinking not in terms of let me get all the resources once and hoard them for the lifetime of my project, you want to get yourself to a more flexible mindset and think in terms of how dynamic can I make my app? Can I simply allocate the resources, use them when I need them, release them back when I'm finished? So a really good basically consequence of both the abstract resources and the on-demand provisioning is you put those two together, you get this ability to scale in minutes. So you can think about scaling your application out to add more resources, or scale in to take those resources away as your needs change. You might be doing this in response to some changes into load or to traffic, Or maybe you do different types and amounts of processing at different times. Maybe you have end-of-day processing, end-of-week processing, end-of-month. Maybe you have situations where your traffic grows dramatically in response to some external event that's either a scheduled event, you know that it happens, or it might be just some kind of interesting event happening somewhere around the world, and suddenly a lot of traffic is driven to your system or to your website. Either way, the cloud gives you this ability to scale in minutes, and this is really an important thing that you need to think about as you're building your application. So with this ability to scale, you're certainly not going to pay for an infinite amount of resources when you're only using some finite amount. So you have a pay-on-consumption-based model. You start paying for resources at the point when you start allocating and consuming them, and then at the point when you shut them down, you are no longer billed for them. So one thing that comes up when I talk to a lot of folks about this, and one neat consequence of this for you as an architect, you now have the ability to control the overall cost effectiveness of your applications. And this turns out to often be a good career and growth opportunity. So instead of simply being the technical master and being able to design awesome systems, which is a great skill to have, you can also start thinking about business value and efficiency, and you can start saying the designs I have are actually X% more efficient than the naive design, and you can actually iterate and improve those designs over time, so that often as you continue to scale up, you might find that you're actually adding economy, adding efficiencies. Maybe you can actually scale up while actually not increasing the bottom line cost of the resources that you consume. So as an architect, think a lot about not just the economic value that you bring to your business, but think about ways you can actually use the cloud in really interesting and creative ways to actually optimize your consumption of those resources. Now the last attribute, and I have to admit this one is really my favorite feature, and to me this actually defines the cloud. The cloud is based heavily on access to script infrastructure. You can fully automate it using APIs. So at the very fundamental level, when you approach the cloud effectively at the bottom, operations like setting up networks, setting up routers, allocating IP addresses, launching servers, creating disk volumes, attaching those volumes to servers, and then at the end of their useful life, when you no longer need them, detaching them, deallocate them. At the basic level of the cloud, you can write code to manage all those things. Now, quite often you're going to be using command line tools or visual tools or some sort of automation, some sort of management consoles that are going to build on top of those APIs to simplify it and to further automate it. But the thing that I would like you to take away from this is that at that most fundamental level, you do have the power to automate and to script all the different resources that I show you. We do actually have a number of different SDKs, software development kits, if you actually do want to tap into the cloud APIs and make direct calls yourself, and those are all available to you on our website. Let's take a quick look at the various components of the Amazon Web Services. Now, this talk is not intended to be a detailed introduction to all the different parts of AWS, so I'm not going to spend a lot of time here. I would refer you to our website if there are specific things that you need to know, specific types and kinds of services. At the top level, we're going to find your application that you're going to build using various services pulled from AWS. At the base level, you're going to rely on our physical infrastructure. So the physical infrastructure is spread out around the world. We currently have 9 separate locations that we call regions, located in North America, South America, Europe, and 3 areas around Asia Pacific. You always choose a particular region to operate in. So that means you're going to choose some geographic place around the world. You're going to store your data there. You're going to process your data there as well. A defining feature and something really important to keep in mind, especially as your security folks start to get into your conversations regarding your use of the cloud, once you choose to process or store in a particular region, we're never going to move or copy your data from region to region. You pick a location, your information stays there, and it's up to you to move it from point to point. Now, we do give you tools and APIs to make that migration really, really simple, but you need to really be very confident in your understanding of the fact that motion of data from location to location, that's always something you have full control and full visibility into. So within the regions, we have a number of physical facilities per region. We call these availability zones. Each availability zone in a region is comprised of multiple data centers. So in a particular region, you might find anywhere between 2 and 5 separate availability zones. We sometimes call these AZs for short. So each AZ, and let's try and take the simplest case where an AZ would be an individual data center. Each AZ in a region is going to be situated such that it has independence from floods and from earthquakes that might affect other AZs in the same region. It's going to have power, cooling, network connectivity that are going to be independent from AZ to AZ. And the important thing about all this redundancy is that when you start to think about designing an application, you're going to start by saying, let me pick a region that's most appropriate based on the locations of my users, based on any particular needs I have to be situated in a particular location around the world. And then you're going to start thinking about reliability and fault tolerance. So what you're always going to want to do is you're always going to want to have some processing resources in at least 2 separate availability zones in a particular region. You do this because we've designed independence in the AZs to make sure that any kind of a physical event or a connectivity event that might affect one AZ in a region, the odds are it's not going to affect the other AZs in the same region. So by situating your processing across multiple AZs in the region, you add you make an application that's far more fault tolerant against any AZ level of failure. We also have another kind of physical infrastructure called an edge location, and we currently have 42 of these separate edge locations. The edge locations are used for our edge services, and our current edge services are CloudFront for content distribution and Route 53 for domain name services. Building up from there, we have services for compute, for storage, for networking, and for database. As I build up this diagram, as you see this ever-growing list of services, rest assured that no particular application you build is going to use all of these services. Your job as an architect is to have some level of understanding of each of the different services, and then have a great understanding of when would you actually choose to use, for example, EC2 when you need some processing, or Elasticache when you need some caching between your application and your database, and so forth. It's the very, very rare application that's going to use the majority of these services. Think of this more as a menu where you're going to pick and choose the different services that make sense for each of your applications. I always advise new architects and folks that are new to AWS, don't even try to master the entire set of services with your first application. Pick 1, pick 2, get that first application up and running, and then as you start to either build your second application or you iterate on the first application, think in terms of slowly scaling up the number of services that you use. There's a wide variety of services. We add additional ones on a fairly consistent basis. And so that as an architect, again, have some familiarity, understand what they are, think about ways that you would actually put them to use, and then dive deep on individual services as your needs expand. So the first level was the infrastructure building blocks. The second level are a bit higher. These are platform level building blocks for doing things like parallel processing, content delivery, media processing, messaging, and email. Building from there, we have a number of cross-service features, things that are not particular to an individual platform or infrastructure service, but instead these things run across all the different services. Things like the identification and access management, IAM, where you are able to construct accounts and set detailed levels of permission for those accounts. Or Amazon CloudWatch for monitoring, where a number of the services report either statistics either every minute or every 5 minutes to CloudWatch. You can monitor the health of the services. You can set alarms. You can set alerts. You can use these to drive auto-scaling up or down based on the performance, the health, the overall throughput of your service and your system. And then a number of different deployment and automation services, the Elastic Beanstalk, OpsWorks, CloudFormation, and simple workflow. At the uppermost level, we have a number of different tools to let you access your services and to build. Libraries for a number of different languages. The AWS Management Console is your web interface. Tools and toolkits for both Eclipse and Visual Studio, and then command line interfaces that run both on Windows and on Linux-based systems. Okay. Now, one thing that's really important when you start thinking about architecture and fault tolerance is to have a bit more understanding of the fault tolerance level of the various building block services. Some of the services are what we call managed services. So within the implementation of these services, beyond the scenes, we have built-in redundancy, built-in fault tolerance. The services are actively monitoring themselves, detecting faults, and fully failing over without you having any real awareness of that happening on your part. So these tend to be the kind of the mid-level to higher level kinds of services. So the other services, the ones listed on the right, these are a little bit closer to the metal. You can absolutely use these to build fully fault-tolerant systems, but by the nature of these services, there's going to be a little bit of visibility into your application. For example, if you're using an EC2 instance, you think of it as a virtual server, using one of those virtual servers, hardware can actually fail. If hardware fails, your application has to be able to detect, recover, and continue from those kinds of failures. So some services are inherently fault-tolerant. Others are going to take a little bit of work on your part to be fully fault tolerant. So a little bit of architectural work, and we'll talk about some of that today. So let's talk about scalability and what scalability means in practice. So you're going to, if you are going to actually have an application where the amount of resources deployed is going to change, you're going to need a scalable architecture to take advantage of the scalable infrastructure that you have available to you. So what do we mean when we talk about a scalable service and a scalable architecture? So first we're going to think about what happens when we add resources. If a system is truly scalable, we're going to add additional resources. We're going to get a proportional increase in performance. If we're running with one server and we add a second server, we would hope under the best case that we're going to actually double our performance. We're going to find that a scalable service is operationally efficient, that it doesn't have an overwhelming amount of actual individual personal manual attention needed to keep that service up and running as it scales. We're going to find that scalable services are resilient, and we're going to find that actually the ability to horizontally scale, meaning that instead of using bigger and bigger and bigger machines, this ability to use more and more of them effectively in parallel, often in a load balance fashion, is going to make us able to be very, very resilient. Because if we have 10 or 50 or 100 servers running, if we have a system architected in such a way that if one of those were to fail, the other ones can keep on going. The automation that we'll put into place will simply detect that, take the failed server out of service, and put a replacement into operation, quite often without you even knowing about it. Well, one of the things you'll learn as you start to get experience with the cloud and with AWS, you actually gain a lot of confidence in your service and in its resiliency. You'll find that you can actually, instead of kind of being a bit nervous, a bit concerned about potential failures, you design the system for failure, and you actually go in and you explicitly and purposefully introduce failures into the system to actually measure and to observe its response to different failures. We'll also find that there's a measure of cost effectiveness, that you'll find that scalable services become more and more cost effective as they grow. One interesting factor of this is that because you don't treat your servers on an individual basis, you treat them just as basically this undifferentiated array of processing resources. We generally find that our most successful customers do not really kind of hand touch and hand tune and log in to each individual server. They treat these servers as replaceable resources. They don't give them individual attention. If a server starts to malfunction, they will generally take it offline, put in a replacement, and then diagnose at leisure rather than trying to fix running resources. So that'll, in terms of both operational efficiency, and the amount of manpower you need to invest, you're going to find that both of these are going to lead to a more cost-effective model for you to run. Let's talk about an important, these are the main set of lessons we're going to talk about today, the 6 principal lessons of cloud architecture: designing for failure, loose coupling, implementation of elasticity, use of security, use of parallelism, and the ability for you to leverage different storage options. Let's talk about what design for failure means. So Werner Vogels, the CTO of Amazon.com, he very famously said a couple years ago, he said, everything fails all the time. So this is not meant to cast aspersions on the quality of any particular piece of hardware or software, but if you do a time at some point fail. If we take this as a basic design consideration, if we assume that everything is going to fail sooner or later, we want to actually think about that at design time. And if we design for failure, if we say, well, failure is just simply a part of the normal operation of our system, we know that sometimes things are going to break. And if we simply say, let's plan for that from the beginning, let's think about it, let's make sure that we have no single points of failure in our system, and from there, let's do what we call designing backward, from the fact that we want to provide something very robust, very highly available to our ultimate user. Let's work backward from there to the actual underlying physical architecture and implementation. What does it actually take to make sure that if a piece of hardware fails, if something is removed from operation, or if it's replaced, if we can actually say, let's just make sure that we have upper-level systems and architectures that paper over any of those momentary losses, detect, recover, isolate, and simply keep on going. So let's take a look and see what AWS provides to make that easier for you. We give you a number of services that are themselves fault-tolerant, as we talked about. So there's just simply a lot less things you have to worry about when you have things like elastic block storage snapshots. So when you create virtual disk volumes with the EBS service, you can, in addition to the built-in RAID-level redundancy of each EBS volume, you can very, very easily take snapshots. You can script that and automate it to take regular snapshots on a time basis, or you can simply use the APIs or the console and take snapshots at any point that you like. So if you have some long-running processing, you might choose to take snapshots before and after to capture the state of your application around that. The AWS auto-scaling service. The interesting thing about auto-scaling is that the first thing people look at auto-scaling for, they say, well, this is a great way for me to respond to a changing load. And indeed it is. The auto-scaling is perfect to let you scale up and scale down. You can look at any of the different metrics on your system and use that to drive decisions to add processing resources or to take them away. That's great. But you can also use auto-scaling with just a slightly different configuration. You can say, please make sure that I have at least this number of servers running that are actually working on a particular part of my business. So when you create an auto-scaling group, you can figure in both the minimum and maximum number of servers you'd always like to have running in that group. The auto-scaling service will take care if you have a group and maybe you configure the group to be 10 servers. If a server were to fail, the auto-scaling will say, oh, a server's failed, I'll launch a new one with the specified configuration and setup information to keep that group at the desired level. Our database services, the relational database service, has an option that we strongly recommend. You can run the database in 2 availability zones simultaneously. If you select the multi-AZ option, we will launch both a primary and a secondary database for you. We'll automatically synchronously copy data from the primary to the secondary. We'll monitor, we'll institute automatic recovery if something happens to the primary or to the secondary. We've talked a bit about the fact that you always want to provision your application across multiple availability zones. And we give you a number of different tools to actually make it easier and easier to run across multi-AZs. Things like both the auto-scaling and the elastic load balancing make it very straightforward for you to have functionality across different AZs in the region and to apportion traffic accordingly. So design for failure, important data point there. Another really important point, and this gets as you start to be more and more complex in your aspirations and your system building, you want to make sure that the different parts of your system are connected together as loosely as possible. So, and generally this means that you're going to have a number of independent components. You're going to define those components as individual black boxes that talk to each other through message queues or through asynchronous defined interfaces of some sort. You're going to try to decouple these black boxes from each other as much as possible. And you're going to think in terms of the ability to scale individual phases of processing pipelines using clusters of machines. One of the primary architectural models we see these multi-phase pipelines. Now, in the tightly coupled model, you'll have a number of processing stages, which we here have labeled as controllers. The tightly coupled model means that controller A is going to pass data on to controller B, onto controller C in some kind of a synchronous fashion, probably by making some function calls. And the problem with this model, as you get more and more moving parts, as you have more stages, you have more opportunities for things to go wrong, and you'll find that this system is going to actually run at the speed of the slowest component. If one of the controllers gets momentarily behind, if it gets stuck for some reason, that backlog is going to quickly propagate itself through the entire system. So in this tightly coupled model, a single issue, a single slowdown is going to result in the entire system getting stuck. What we recommend instead is to use a queue-based model and to implement loose coupling. Simple queue service makes it very, very easy for you to actually separate each of the different control steps of your system with a message queue. The message queue means that each of the controllers is, instead of having API-powered access and having it in turn call APIs to the other stages, it's going to be a simple stateless process inside the controller. That process is going to read a request from a message queue. It's going to do whatever that is, whether that is to process an account or a transaction, transform an image, do some kind of whatever is the work unit. It's going to do that work. Once it's done its duty, it's going to then write the next piece of work to be done to another message queue to be picked up by the next controller in the pipeline. This architecture has a number of important benefits and implications. One, if some of the controllers are slow or stopped entirely, not a big deal at all. The messages will simply accumulate in the message queue. At the point when the controller is ready and back online, it can then start processing the backlog through the message queues. In most cases, you have the ability to have multiple controllers processing a single message queue. So if you find that the controller B, for example, is a little bit too slow because there's a lot of work to do and it's kind of getting behind, you might be able to think about launching multiple copies of controller B, each pulling from the same input queue and each writing to the same output queue in order to work through the backlog. So you could even think in terms of auto-scaling and thinking each of these controllers A, B, and C is actually an auto-scaled array of controllers that's going to scale up and scale down in response to the backlog or to the queue size. All right, now elasticity is a fundamental property of the cloud. So a couple of things that you think about when you think about elasticity. Don't assume that all of your components are healthy. Don't assume that they're running at fixed addresses or locations. Think about designs that you can build that are resilient to rebooting and relaunching. So for example, you want to think about when your instances start up. You want to think about that instance starting up, having the environment supply it with some configuration and some identity information so that when that instance launches, it can consult the environment and it can say, what kind of server am I? Am I a web server? Am I an app server? Am I a database server? What is my role? What is my identity? And then have it configure itself based on that information. With AWS, with our EC2 service, you have the ability to actually do configuration at a number of different times in the lifetime of that instance. You can make a fully static configuration where you pre-bake all of your configuration into a machine image. Or at the other end of the extreme, you can make a fully dynamic configuration where you launch generic images and then configure those totally at launch time. There are some trade-offs in either one as far as what is the level of flexibility I have, what is the amount of time from when I say launch to when it's fully installed and fully running. But this idea of dynamic configuration is something that you want to think about when you are thinking about the right way to architect your application. Some AWS services are going to help you here. You're going to use auto-scaling, and you're going to use auto-scaling driven on metrics. So let me talk just for a second about what I mean to use auto-scaling on metrics. As I talked about before, each different AWS service exports various system metrics to our CloudWatch monitoring service. So for an EC2 instance, this is going to be things like the network traffic in, network traffic out, number of disk reads, number of disk writes, and CPU load average. You can then take those metrics, you can then set some rules for the auto-scaling, and you can create rules that, for example, might say, looking out across all the CPUs running in my auto-scaling group, I'd like to make that group bigger if my load average is 80% or more for 5 consecutive minutes. So that would be a scale-up rule. So you can say, add another server every time my servers are 80% or more busy for a 5-minute period. You then have a corresponding scale-down rule that says, if all those servers in the group are 20% or less busy for that same 5-minute period, I'd like to actually remove one of those instances from the auto-scaling group and terminate it. So that auto-scaling is going to give you that elasticity. We have another service called Elastic Load Balancing that works into auto-scaling, so that every time auto-scaling adds a new instance to the group, it informs a load balancer, and it says, please start routing traffic to this instance as long as it's healthy. You might think in terms of an architecture, we actually have multiple load balancers, a primary load balancer at the web level, and then secondary load balancers in front of applications and application services to load balance across multiple instance types. Think about storing configuration information in our SimpleDB service or our DynamoDB service to bootstrap the instance. And you also want to think about using configuration management tools. There's various open source tools like Chef and Puppet and Ansible are all great tools you can use for configuration management that will help you to launch from generic instances, install packages, configure, set everything up at launch time, if you'd like. Some other elasticity concerns and issues. Think about building systems that are resilient to rebooting and relaunching. You want to think about that it should not be a big deal in your mind. It should not really be a big deal in terms of your system architecture if some particular server happens to relaunch and restart. That shouldn't be a cause for any kind of concern. It shouldn't give you a heartache. You shouldn't think, oh my, the server might reboot. How horrible. You should think at a certain point after you've successfully built a fault-tolerant, resilient architecture, you should have some level of confidence that says, okay, if something fails, if something breaks, no big deal. I've been through this test. I've tested this. I've rebooted it a number of times. I know that all the pieces are going to come together very, very nicely, and it's going to put itself back together automatically. There's actually a service called the Chaos Monkey I'll talk about in just a bit that can help you to add and test for this resilience. Think about making stateless components, which you can put in the message queues we talked about earlier. Makes it very easy to run multiple copies in parallel. We talked about this idea of taking your application functionality, packaging it into a machine image so that you can launch multiple copies as needed. And then, again, decoupling, isolating components using the simple queue service. Moving right along. So our friends at Netflix built this really interesting application called the Chaos Monkey. So the Chaos Monkey, and you could use this either in your development stack or your production stack. The idea of the Chaos Monkey is that it's going to simulate a fairly high degree of chaos and failures within your running application. It's going to shut down instances. It's going to perturb network settings. It's going to effectively go in and at a configurable rate and with a configurable level of seriousness, it's going to actually go ahead and basically break your environment in different ways. So this is a way to actively introduce faults and failures into your environment and to do those at a level that you can see them happening, and you can go and run a Chaos Monkey, see things break, make sure that you actually are in a good position to fix them. At first, you'll want to run this on your development, your test environments. As you gain confidence, and I've actually seen people do this, they run it at a low kind of a background hum level on their production environments. Make sure that the production environments are fully fault tolerant, fully resilient as well. This is one of those things that gives kind of the traditional IT system architects and administrators, they hear about that and say, wait, I'm breaking my system on purpose. That's really, really scary. As we talked about earlier, though, about the design for failure model, this actually turns out to be a great way to build very, very resilient applications. Security is a question that comes up all the time. Our advice here, you don't want to have to add security after the fact. If your company is new to the cloud, you're going to face a lot of different questions from your peers about, hey, is the cloud secure? How do I actually make it secure? You want to think about the security as something you're going to build in at every layer, something you build in from the ground up. We see the security model as a shared responsibility. We're going to do a number of different things for you. We have a number of different certifications and accreditations for AWS. We have a number of security features in AWS. We have recommendations. We have best practices. That's going to get to a fairly high level. But at a certain point, we're going to be launching an OS that you've configured. That OS is going to be running applications that you've configured. So we're going to give you a great secure environment to start with, and then the responsibility passes to you as you get to the higher levels of your application. As you can see in the left, we have worked really hard to get a number of different C's and A's, as our security folks call them, the certifications and accreditations. That's a subset of the full set that we have available to you on the left. If you go to the AWS security website, which is aws.amazon.com/security, you'll find a lot more detail about the various C's and A's that we have. You'll also find a number of white papers, recommendations that will help you to walk through the various security challenges and options you have available to you in AWS. Recommendations that we recommend encrypting data both in transit and at rest. Recommend you be very, very careful with your AWS credentials. Rotate your keys on a regular basis, and make sure that you've actually done a good investigation. You have a good understanding of the various security options available to you at the application, the OS, the stack, and the image level. We give you services like IAM, the Identity and Access Management, that let you create individual user accounts, which you could use for either logged-in users of your AWS console or for the applications. Or you can create IAM accounts and use those to actually represent individual applications. With these accounts, you have very, very fine-grained control of the exact set of both service APIs and service resources that are accessible to a particular account. Multi-factor authentication, the virtual private cloud, policies for your storage, security groups, encrypting file systems are all additional security options that you have. This diagram just shows you some of the different points where you might actually choose to exercise security. You have the concept of security groups, and you can control, with a security group, you have the ability to control both inbound and outbound traffic. You can restrict to particular ports, protocols, IP addresses, and even IP address ranges as well, using the various security groups and security group features that are available to you. For example, you might choose to make your web server open to access from anywhere in the world. You would then, at the interior levels, your caches, your databases, your application servers, you would allow access to those only from within the cloud and only from specific instances that you own and you run and operate from within the cloud. So we give you a lot of control, a lot of flexibility with the security groups. It's then up to you to take those and apply those in a very stringent, tightly controlled manner to actually implement your security policies. Thinking in parallel. So we talked a lot about elasticity and scalability. So doing things serially and sequentially, that's the old way. The parallel model says you're going to use various combinations of multiple processing resources side by side to get the degree of throughput that you need. You're going to think about multi-threading. You're going to think about concurrency. You might think about doing MapReduce jobs using our Elastic MapReduce service. We talked already about Elastic Load Balancing to scatter load across multiple services. And you also want to think in terms of, to get parallelism and to also, this factors into scalability, think about taking a job, decomposing it into its simplest form, and using those kind of simple components as the units of scalability and of parallelism. A couple different AWS features that will help you to get parallel. We have the Elastic MapReduce, which uses Hadoop, a popular open source framework, to let you do large-scale distributed processing where you might want to use tens, hundreds, even thousands of systems in parallel. We have, at the high end of the different EC2 instance types available to you, we have a number of different cluster compute machines with high-end Intel processors, many cores, large amounts of network connectivity. We have something called the spot market, where you can place bids for compute power. You have the ability to expand or shrink your parallel clusters, and you put this all together, you can create an elastic supercomputer where you can scale up, scale down, process any amount of data very efficiently and very cost effectively. With AWS, you get a huge number of different storage options. We have Amazon S3 for static objects, CloudFront for content distribution, both SimpleDB and DynamoDB for NoSQL style data indexing and querying. On each EC2 instance, you have local storage. You have elastic block storage, which is persistent storage, virtual disk volumes that you can create and easily snapshot. And then we have the relational database service, which is an automated managed service that actually makes it very easy to launch both MySQL, Oracle, and Microsoft Windows SQL Server databases. It's a managed service, so it's going to give you fault tolerance. It's going to be very easy scalability, automated updates of the OS and the database, easy snapshot backups, easy recoveries as well. And then we have Amazon Redshift, a data warehouse service that lets you create very, very large-scale data warehouses. There's a huge number of different options that you have for storage. This table I put together gives you a little bit of the set of choices that you have. There's different processing options as far as what store, relational, non-relational, many, many different choices you have available to you here. So we talked about designing for failure. We talked about loose coupling. We talked about elasticity. We talked about security. We talked about thinking in parallel. And we talked in terms of storage options. Let's go through a couple questions as time permits. And let's see what we've got here in terms of questions. All right. Oh, my. We've got a lot of questions. I'm not going to be able to get through all these questions. I'm going to pick and choose the best. Give me just a second here, get my screen adjusted. Okay, so let's see. There's a question that says, must we use Amazon CDN or can we use an existing contract with another provider? So there is no requirement that you use our CDN. AWS is a set of different building block services, so you can pick and choose the ones that you'd like. If you have an existing CDN provider, you can certainly use AWS as the origin server behind that CDN. I'm sure a number of our customers are doing that as well. There's a question about, let's see, if the requirement is to build a DR environment, disaster recovery, can you explain the APIs to architect the redundancy across multiple regions? Sure. Okay. So great question. So a couple different things come to mind here. We have a service called CloudFormation. CloudFormation lets you actually encapsulate your entire application stack, all the different AWS resources, your servers, your databases, your message queues, your IP addresses, and essentially describe that entire application stack in a single text file template. Once you have that CloudFormation template built, you can instantiate multiple copies of it within a single region, or you can move that template from region to region. And so let's say you have a system architecture designed and you've actually encapsulated it as a CloudFormation template. You take that template, and for disaster recovery, you can simply launch additional copies of that entire stack across different regions. You might build the stack in such a way that it's parameterized. So you might have, let's say, a small versions for development or test, and then a full-scale version for production. Okay, so that's a very easy way for you to get your architecture moved from region to region. You can also think in terms of moving data from region to region. We give you commands and APIs to let you move things like EBS volume snapshots and machine images from region to region. So when you start to think about DR, you're going to think about how much downtime can I tolerate? What is my recovery point? How far back in time do I need to go to recover my data? So you have a number of different choices with your database snapshots. You can take snapshots of both your Redshift snapshots from region to region, use those to recover as well. All right, so there's a question about multi-availability zone configurations. So the question is it a best practice to add one server per zone when scaling up and subtract one server per zone when scaling down? In general, what you want to do is you want to maintain a reasonable balance across the different zones as you scale up and down. You never want to have all your eggs in one basket. You don't want to have all the servers in the same AZ. I believe our autoscaler actually has a built-in policy mechanism where it's going to make sure that it's going to do its best to keep your servers balanced across the different zones. And let's see. There was a question about will the recording be available? I do believe the recording will be available, and we'll send out an email afterward. And let's see, question, is there a way to do auto-scaling based on the number of items in an SQS queue? Yes, there is. So with SQS, it actually does report a metric to CloudWatch. And so what you would do is you would watch that metric, and you'd use that metric to basically say scale up or scale down based on the number of items in the queue. So what you'd have to have a good sense of is the queue size under normal operational behavior, kind of a sense of what is my arrival rate, what is my processing rate, what is my desired transit time of a message from when a message arrives, message is processed to when the results are available. And then you want to use those factors as basically a guideline to where you would set your queue service to, your scaling. Let's see, number question here. What is a good technique for rotating keys? So the first thing you want to worry about is you want to have your keys in as few different places as possible. I see that the thing to avoid is to actually embed keys in source code and to check in keys into source code control. It makes them too difficult to find. It also makes you a bit more vulnerable because you don't know exactly all the different places where your keys are stored. We give you services with the identity and access management. We have something called roles, which you can often use as basically an indirect way to access your keys. I'd also recommend using things like the security token service as another way to have keys stored at as many locations or as possible. Keep that to a minimum. And then if you go into your AWS account, you'll see that you're actually allowed to have two sets of keys active at any given time. So the idea here is that in practice, you can't make an instantaneous switch over from old keys to new keys. So you can always have a current set of keys, and then you can go in and create a second set of keys. Take that second set of keys, embed those, put those in all the locations they need to be, restart the affected services so they can authenticate themselves with the new keys, and then you can disable the old set of keys. Let's see, one embarrassing question here. Why didn't you mention DynamoDB on leveraging storage options? Purely an omission on my part. I actually didn't update the slide properly. I will do that after the fact. Question about where can we find more about the AWS security architecture? if you go to our security center, which is aws.amazon.com/security, you'll find a number of best practices white papers, recommendations, a lot of details on what we recommend for security architecture. And it looks like that is just about everything. Let me do one more refresh here. Looks like that is all the questions. If there are no more questions, I would like to thank you for attending. I hope this has proven to be a great use of your time. And so thank you very much. Let me just pass you along to the contact information here. Hang on just one sec. Okay, we've got a slide here for additional info. Yeah, there we go. So there's our Architecture Center. My AWS blog is linked there for you. And then AWS Premium support is available to you for architectural consultations as well. And with that, I'd like to thank you for coming. My email address is there, as is my Twitter handle. And with that, I will wrap up our webinar.
Great. Thank you, Jeff. I'd like to extend special thank you for all the people who attend Webcast today. And then please take a moment to fill out our survey. We really appreciate your feedback. So thank everyone for joining. Have a great rest of your day.